Okay, everybody, welcome back to AP Physics. Today I need your attention because we're talking about, the question I'm about to answer is work and potential energy. How do you get that? Well, this is how you get it. If you have a spring and you take your hand and you force on that, and you're an alien, and you force on that spring, do you work on that spring? Yes, you do, because you force it over a distance. Do you agree? You force that over a distance, and then you have compressed this spring. Now, what does the spring have now? Potential energy. And so that's how we can say that the potential energy of a spring is equal to the work done on the spring, but also is equal to the work that a spring can do on an object. Because once the spring, so if there's a little object on here, the spring will force in that direction over this distance, and the spring will work on the object, and that's how this potential energy of a spring is equal to the work that a spring can do as well. And keep in mind that work then is the ability to change energies. Okay? You can think of it that way. So how does all this work? Okay, so let's just say that we have a gun, a spring-loaded gun that has been depressed a distance of 3 meters. This is a huge gun. It's an art gun. And you have a large dart here, okay? And we'll say that the dart is 2 kilograms. Okay? And so we'll say that the spring constant is 2,000. Okay, 2,000 newtons for every meter I compress it. Okay? So the first thing we have to figure out is, once we get down to this x position here, what's going to be my max force? Well, it's going to be kx, which in this case is going to be 6,000 newtons. Now, ask yourself, is that enough force to move that 2 kilogram dart? Yeah, because you need 20 newtons to just level it off with gravity, right? So the question is then, how high is this dart going to go? So how high, right? So you're thinking, oh, this is potential energy due to gravity, right? And that's going to be mgh. And you'll say, well, the potential due to gravity will be, it'll be according to how much kinetic energy it has right here at the bottom, right? So whatever the kinetic energy is right before it leaves the gun will be equal to the potential. And that kinetic energy will be almost, in this case, equal to the potential of a spring. So if you were just a regular physics student, you could say mgh equals 1/2 kx squared, and you could solve for h by saying, 0.5 kx squared divided by mg. Do you agree? But the advanced physics student would say, I'm going to lose some of this potential energy of the spring. How come? The advanced physics student says, well, geez, the summation of forces here is the force of the spring minus the force of gravity of the dart, right? Because if the spring was just enough to hold the dart, then there would be no acceleration. So in reality, the summation of forces then in this case would be kx minus mg, and that would be the force that works over a distance. So you would have to consider that if you were talking about kinetic energy. But now let's think about talking about just using this formula here. How could we work this around so it actually made sense? Because I'm not really, I'm not really concerned about kinetic. That's not kinetic either. Where is kinetic? I guess I'm not concerned about it. That's why it's not there. Right? Because really what I'm doing, if you think about it, is I'm changing my potential. So this right here would be a change in potential. That would be equal to mg. But instead of saying h, the way it's labeled, it would have to be h plus 3. Does that make sense? Because the spring is actually first bringing it up 3 meters before we get to what we have defined as our h. Right? So in order to do this, then, we would say, hey, I can do this. My potential of the spring is equal to my potential due to gravity. This would be at the bottom, you know, and then versus in the top. So 1/2 kx squared is equal to mg h plus 3. Because I have to move it up that potential just to get it out of the bullet, or just to get the bullet out of the gun. Does that make sense? We didn't do this in regular physics, but we're doing it now. Okay, so you can probably deal with that then, right? At this point, do I have to do any more? No. So let's look at another one. Okay, so let's say that we have a table, and we have our spring attached to a wall here, and let's say that I put a ball in the spring, and I've displaced the ball, let's say 4 meters. Okay? My question then, the typical AP physics student can answer by the time the AP test comes around, or in your case, by next week, is how far in the x direction does it land? And we'll just say that we have a height there. I better give it a number, 4. Okay? So, you should know that x is going to be equal to velocity in the x direction times a time that it takes for the thing to fall, right? Okay? So our x is going to be equal to, well, I don't know the velocity in the x direction now. But I know that I have a potential due to the spring here, right? And that's 1/2 kx squared. And that, at this point, is going to turn into what kind of energy for the ball? Kinetic energy, minus, any thermal energy lost in the spring, which if it's an ideal spring, there's no thermal loss either. So that's going to equal 1/2 mv squared. We can see how nicely that cancels out. And v equals the square root of kx squared over m. And then that's the mass of the ball, right? Because that's the thing that's going to be moving. You agree with that? Okay, so we better give this k. We'll just say the k here is 100 newtons for every meter. So our velocity and the mass of this ball, we'll just say is, 1 kilogram. The velocity in this case then is 100 times 16 divided by 1. Velocity is 400 meters per second, unless I did that math wrong. That's pretty fast, right? But it's not quite 3 times 10 to the 8, so it's still possible. Okay, so now the question is, how far is that going to go? Well, it's going to go quite a distance, right? Because the time that it takes to fall is going to be equal to the square root of, 2 times 4 over little g. Do I have to show that anymore? Square root of 0.8, if I did that math right. So now I know that the displacement is 400 times the square root of 0.8. And I can figure out how far it went. Do you agree? 49.9? Yeah, this is 40. Okay, so it's 40 times the square root of 0.8. Can you do that problem? Oh, yes, you can. So let's look at one more, unless you have a question. Okay, so one more problem here, and we're just going to try to figure out how far it goes away from the edge of the table here. So I'll let you guys work on that for a minute. Okay, so the question was, what's the mass of the ball? We said it was m. Okay, so we have a potential of the spring that will be released here into kinetic, and then we have a potential due to gravity that will be released into more kinetic. Okay, so we could really say that the potential of the spring plus the potential due to gravity is equal to a kinetic at this point, right? So it'd be 1/2 kx squared plus mgh equals 1/2 mv squared. Okay, that mass cancels out, divided by m if you want. Okay, so we have 0.5 k, and it's a little k where the big k is for the kinetic energy. X squared over m plus gh equals 0.5 v, so squared. So v at this point, v equals the square root of kx squared over m plus 2gh, if I did my variable math correctly. So the variable math checks out. Don't put numbers in there, I'll screw it up. So that is my velocity at this point, is kx squared over m plus 2gh, the square root of that. That's my velocity, okay? And that'd be my velocity in the x direction. So that would go down into here. And then my time, because displacement equals velocity times time, would be then the square root of 0.8 again. And that's how I would figure that out. Any questions? Okay, so you see that the longer you keep yourself in big variable form, the more directed your math becomes. And I didn't even have to, you might have been thinking I'm going to solve for kinetic energy, but you can cancel that out. So try to organize yourself according to big variables first. Tell yourself a picture with your math, or a story with your math, and then everything else just falls in line. Okay, hopefully that helps for your assignments this weekend.